Hi, and welcome back to Codex. Our speaker today is Pete Casazza from the University of Missouri. Professor Casazza is a world expert in frame theory and Banach space theory. Today, he will tell us about piecewise scalable frames. Take it away, Pete.
Okay, we can go forward. I wasn't sure everybody, was completely familiar with frames. So I thought we'll spend a few minutes just looking at frame theory. So we have a family of vectors in an n-dimensional Hilbert space Hn. This also works in infinite dimensions, but that's extremely more complicated. So today I decided to just do finite dimensions. It's a frame if there's constants A and B satisfying this inequality. We can go on. If A equals B, we call this an A-tight frame. And if A equals B equals 1, this is called a Parseval frame. It's called a Parseval frame because if A and B are 1, we actually are getting Parseval's identity, but for a redundant set of vectors instead of a basis. Next. And this is actually what I was just saying. This is a Parseval frame if we actually have Parseval's equality. The difference here is we've made no assumption about this being literally independent of basis, orthonormal basis. You can see, for example, and there's no restriction on redundancy. So I could take an orthonormal basis and write it 3 times. It'll satisfy this inequality. A and B will then be 3 instead of 1. Next. The largest A and smallest B satisfying this inequality are called the lower and upper frame bounds. Next. We also will be looking at Riesz bases. This is if there's constants A and B satisfying for all real numbers BI. We have this inequality. So if you look here, this inequality is actually making this basis look like the unit vectors in L1, but L2, I mean, but without equality. Next. Every frame has something we call an analysis operator. It maps the Hilbert space over to L2, M, where T of X is actually the M tuple of X inner product with all the frame vectors. Next. The synthesis operator is actually the dual operator. It maps M to M back to Hn, and it maps AI to the sum of AI xi. So in particular, it's mapping the unit vectors in L2M over to xi. Next. The frame operator is T star T. It's the positive self-adjoint invertible operator S given by S of X as a sum of X, xi, xi. So for a frame, every vector, if we look at the sum of X, xi, xi, this is actually an isomorphism on the Hilbert space. Next. We're going to be dealing a lot with Parseval frames. So the following are equivalent. Xi is a Parseval frame. Next. The operator T is the analysis operator is the isometry. Now, isometry doesn't mean onto. The operator T is actually an isometric embedding. 3. For every X, the norm of X squared is the sum of X, xi squared, which I mentioned a minute ago. Next. Also for a Parseval frame, and this is what's important for us, for every X, the sum of X, xi, xi is equal to X. That is, the frame operator is the identity. Now, like I said, the difference here is these xi's are not necessarily linearly independent. Like I said, I could take an orthonormal basis and write it twice, multiply each vector by 1 over the square root of 2, and I'll have this equality. But I actually have every vector written twice. So the difference between bases and frames is that frames are allowed to be redundant. And something else which got me in trouble when I first started here, I constantly made mistakes due to the fact that we have not assumed the xi's are 0. It could be that every other xi is equal to 0. And I used to constantly make mistakes by dividing by the norm of xi and all kinds of stuff until I got used to the fact that in an arbitrary frame, we can have as many 0 vectors as we might want to have. Next. So first we need to look at scalable frames. So a frame xi is scalable if there exist constants C1 through Cm. These are called the scaling constants. So Cixi is a Parseval frame for Rn. Now, a long time ago, around 2000, David Larson asked at a meeting if there was any way of identifying the scalable frames. And after that, a huge amount of literature occurred. So next, a frame is scalable with the constant Ci, means for every x, the sum of x Ci xi squared is the norm of x squared. And next, I think I also put in, I guess I didn't. If we have xi, excuse me, if we have vectors xi and we make them as row vectors into a matrix, the column vectors, it turns out that a frame is scalable if and only if there's a diagonal matrix D for which the columns of the matrix XD form a Parseval frame. Next. There's a ton of literature on scalable frames. You can look at the references in our paper. We'll look at a few of the results here because we need them. So next. Traditionally, frames were used in signal processing all the way back to 1946. But today, frames have significant application to problems in pure math, applied math, engineering, medicine, and much more. So we get quite a bit of support now from the applied math section of NSF. Next. The advantage of scaling a frame before applying is that it gives an exponential decrease in the number of calculations needed for the application. This is, excuse me, because for a Parseval frame, x is a sum of xi for all x. It turns out that the number of calculations needed to do reconstruction with the frame is actually a function of the frame bounds A and B. As the A and B get farther and farther apart, the number of calculations needed to carry this out grows exponentially. And even worse, if you're working with huge frames with maybe 10 million vectors, it's sometimes that there's not enough computing power to actually calculate with the frame. But if the frame is Parseval, you don't need any calculation. Every vector already has a exact representation, sum of x, xi, xi. So, yeah, sorry. I meant to leave the phone in the other room. The point is that if I have a frame I want to use for applications, if I could scale it first and make it Parseval, then I can significantly reduce the amount of effort it takes to deal with the frame. So this is sort of the advantage of scaling. Next. A two-vector frame in R2 is scalable if and only if the vectors are orthogonal. That's essentially obvious. Next. An element frame in R2 is scalable if and only if the vectors do not lie in some open quadrant cone, say the red area here. So that means that I could have an arbitrarily large number of vectors, but if they lie in this cone, they can't be scaled. Actually, something I forgot to put in here, which let me just mention. If you have a huge number of vectors you want, like 1/2 n, n plus 1 in an n-dimensional space, a randomly chosen frame is actually scalable. I forgot to mention that, but in here, I just noticed this morning that I had left it out. Next. So 3 vectors in R2 are scalable as long as they do not lie in this open cone. Next. For m greater than equal to 3 vectors in R2, which are scalable, scaling is done by choosing 3 vectors from the set, which do not lie in an open quadrant cone, scale these 3 vectors, and set all the others equal to 0. Next. So if we had, say, a unit norm frame in R2, they don't lie in an open quadrant. After rotation, we might as well assume theta is bigger than pi over 2 and psi is less than pi over 2. X1 is 1, 0, X2 is cosine theta, sine theta, X3 is cosine psi, sine psi. Next. Then this is the scaling for this frame. So the important thing is that you actually have a formula for the scaling. It's not that there's just some abstract nonsense that says you can scale this frame. You can actually write down the scaling and therefore you can use it if you need to use it. Next. Suppose you have a unit norm frame not lying in open quadrant. After rotation, we now may assume the vectors look like this. Next. There is a t, so that if A1 is this, sine t, sine 2 beta minus 2 alpha, etc., this will actually turn this into a Parseval frame. So it is actually possible in R2 to scale 4 vectors instead of scaling 3 and then setting all the rest equal to 0. But you can see that this is already becoming quite a mess. And if you get past 4, we actually no longer have any formulas for scaling. Next. A family of vectors in H3 is scalable if and only if they did not lie also in an open cone, but in this time, this is an open quadrant cone. So again, if you're in R3, you can have a ton of vectors, but if they lie in this cone, you can't scale them. This means basically, right, they're all somewhat close to one another within pi over 2 of each other in some cone shape. Now, when I say, I wrote the cone this way, but the point being, if you can rotate this cone anywhere, if you can get the vectors to lie in it, then they're not scalable. Simply because if they lie in some other cone, I could always apply a unitary operator and rotate them all into the cone. A unitary operator won't change scalability. So next. So for a general frame, we choose a subset which does not lie in an open quadrant cone, scale this subset to a Parseval frame, set the other frame vectors equal to 0. Next. So after you get past 4, not lying in an open quadrant cone is not enough for it to be scalable. This is only true in R2 and R3. Next. In these cases, classifying scaling is much more complicated. You have to look into some of the papers. Next. As a simple example, let Xi be a frame for Rn. And suppose Xi of 1, Xi of 2 is positive for all I. That is, all the vectors in my set have the same, have the product of the first 2 coordinates positive. Next. Then if the frame were scalable by AI, we might as well assume the AIs are all positive. Because if you have a Parseval frame and you multiply the vectors by plus or minus 1, it's still a Parseval frame. If we let x be 1, 1, and y be 1, minus 1 with all zeros, now next, the norm of x squared looks like this, and it also equals the norm of y squared that looks like this. Next. And this inequality is going to hold if and only if ai squared xi1 times xi2 is 0 for all I, which is a contradiction because xi1 times xi2 is positive. And if I'm going to scale this with ai, they can't all be 0, or I just turn it into the 0 frame. Next. So for example, if we looked at this frame here, next. This is the Riesz basis, a bad one, but it's a Riesz basis and it's not scalable. For the reason I gave above, although above I required the product of the first two coordinates of every vector be non-zero. It actually doesn't matter if one of them happens to equal 0. The same argument works fine. Next. So given a frame with frame operator S for all x and Rn, next. If we look at the sum of x, s to the minus 1/2 of xi, s to the minus 1/2 of xi, I can move this s to the minus 1/2 around, and I'll discover I'm going to get x. And what this means, I may have written this down next. Yeah. So for any frame Si, s to the minus 1/2 xi is a Parseval frame that we call the canonical Parseval frame. There may be other ways to turn this into a Parseval frame. This turns out to be the only way to do it with an isomorphism. S is an invertible operator, which is positive. So s to the minus 1/2 is an invertible operator. So this is an invertible operator that's turning the frame into a Parseval frame. And this is the only invertible operator that'll turn this into a Parseval frame, if it's not to start with. Next. Given a frame, yi is a dual frame if for all x, x is the sum of x, yi, xi. Now, if xi was a Parseval frame, then we could replace yi by xi, and we'd have the sum of x, xi, xi is x. But if I can find some other yi, so the sum of x, yi, xi is x for every x, then we'll call yi a dual frame to xi. So in particular, s to the minus 1/2 of xi, well, s inverse of xi is a dual frame for xi. Next. So the point being that if we have a frame and we have frame operator s, we can reconstruct every vector by looking at the sum of x, s inverse of xi, xi. And as I mentioned before, the problem here is that computing x inverse, if you have a frame with 1 million vectors or 10 million vectors, s inverse could be quite hard to compute if it's even computable at all. So s inverse of xi is a dual frame for xi, and it's called the canonical dual frame. Next. Every scalable frame has a scalable dual frame. So next. I'm not going to prove these theorems. This is all part of the literature. We'll get to our stuff in a minute. Let xi be a frame for Rn. The following equivalent: ai xi is a Parseval frame. ai squared xi is a dual frame for xi. So every frame that's scalable, it has a scalable dual. The problem here is that the scalable dual doesn't have to be the canonical dual frame. That is, ai squared xi doesn't have to be s to the minus 1/2 of xi. Next. Previous theorem says that a scalable frame has a scalable dual frame. It does not say that canonical dual is actually scalable. It's easy to make an example. Next. in R4, if we look at this, this is actually an orthonormal basis for R4. The inner product of every two vectors is 0. Next. If we were to take the second two columns and replace them this way, now we have 8 vectors. And this is a scalable frame. It's got 8 vectors, but the first 4 are an orthonormal basis, so that alone scales the frame. So this is a scalable frame. But the canonical dual is not scalable because the canonical dual is going to pick up x5, x6, x7, x8, and these are not going to be able to be scaled. Next. So 1/2 xi, I goes from 1 to 4 is an orthonormal basis for R4, and so this is a scalable frame, but its canonical dual is not scalable. I don't think I showed that. It probably takes a little work. Next. So the question is, when is the canonical dual or scalable frame? Well, if xi is a frame with frame operator S, the following are equivalent. Next. S inverse of xi is scalable. Next. This constant AI, so AI xi is x squared. The frame operator for AI xi is s squared. So this makes it actually fairly easy to check if a frame, if the canonical dual is scalable. It's fairly easy to check whether AI xi has s squared as its frame operator. Next. There's constants AI, so that AI s to the minus 1/2 of xi has s as its frame operator. This is an alternative way to check whether this is scalable. It has a scalable dual. Next. There's a number of serious problems with scaling. First of all, very few frames are scalable, as I mentioned, especially in R2 and R3. If the vectors, and in fact in Rn, if the vectors all lie in a cone, you can't scale them. And even if they don't, after R3, it's complicated to tell if they're scalable, and it's extremely complicated to compute the scaling. Next. Most of the scalings that have been done to date set most of the vectors equal to 0. That is, like in R2, you have a ton of vectors, you choose 3, scale them, set the rest equal to 0. So this is an extreme problem for applications. I said we'd like to use this for applications by scaling the frame to a Parseval frame, so the calculations will be reduced exponentially. But if we're using this for an application, we can't set most of the frame vectors to 0. This isn't going to do anything for us. So unfortunately, in most of the settings that we know, they scale by setting most of the vectors equal to 0. And that's not necessarily because they have to be 0, but because the calculations become so complicated, they don't know how to change it to a Parseval frame any longer. Next. There are many equivalences of scaling in the literature. The problem is that all the equivalences to scaling are just what they look like. They're equivalences to scaling, but they're no more easily checked than the original problem of scaling. So the real problem here is, next, give an algorithm for scaling a scalable frame. Now, we're not going to look at this. I don't know the answer. It's probably incredibly complicated. But I thought I'd just mention this is something that would be quite important. If you could give an algorithm for scaling a scalable frame, that would help quite a bit. Next. This problem is basically impossible at this time. Next. Since few frames are scalable and setting vectors equal to 0 is not useful for application, the scaling problem really should be, next. And I raised this a long time ago. Most frames are not scalable, but the real question then is, can you find constant CI so that CIXI is as close to being tight as possible. And by being close to being tight, I mean it has minimal condition number. The quotient B over A, the two frame bounds, is called the condition number. So the real problem here is, given any frame, is there some way to scale it so that the condition number is minimal? Now, this problem is incredibly difficult, as bad as the other problem, at least, and it's actually harder. No one's ever solved a single case of this, except a graduate student of mine and I solved it for R2. But it took 20 pages to solve this problem in R2. So this problem, as far as I'm concerned, is also unsolvable at this time. Next. So I want to look at something that we want to use to replace scalability, because it happens more often and it's more easily checked in general. So we say a frame Xi is piecewise scalable if there exists an orthogonal projection P on the space and constants AI, BI. So AI P of Xi plus BI I minus P of Xi is a Parseval frame. So now we're just dividing this into P of Xi and I minus P of Xi. We want to try to scale each of them and turn them into a Parseval frame. It turns out this is much, much more common, much more easily achieved. Next. If we set P equal to the identity, that means that a piecewise scalable frames are piecewise scalable. So this really is a generalization of scalability. Next. So how can we tell when something is piecewise scalable? It turns out there's 3 direct calculations that need to be done. Next. There exists an orthogonal projection P, scalars AI and BI, so that P of Xi and I minus P of Xi are scalable. So in order to be piecewise scalable, I need to find a projection P so that P of Xi and I minus P of Xi are both scalable frames. That's fairly easy to do, it turns out, in many, many cases. 2.2 is a little more complicated, harder to check, and harder to achieve. And it says that the sum of AI, BI, X inner product with P of Xi, X inner product with I minus P of Xi is 0. Now, this looks like a strange little property. And what it actually is, as I said, if we take a frame, in this case, AI PXI plus BI I minus P of Xi, if we take this frame, make it the row vectors of a matrix, in order for this matrix to be Parseval, the columns have to be orthogonal and they have to square sum to 1. Now, 2.1 says the columns will square sum to 1. 2.2 is telling us that the columns from the AI PXI part are orthogonal to the columns of the BI I minus P of Xi part. And so this condition is what's making all the columns orthogonal. I don't have to worry about the columns of AI PXI because it's a Parseval frame. It turns out its columns have to be orthogonal. And BI I minus P of Xi, its columns have to be orthogonal because it's a Parseval frame. The trouble we run into is when we take columns from AI PXI and try to hit them on columns from BI I minus P of Xi. And 2.2 tells us precisely what has to happen. Next. I already said that, I guess. Next. So in order to piecewise scale, at the very beginning, we have to have AIXI, that should have been PXI, and BI I minus P of Xi, both have to be Parseval frames. And then we have to have this condition. Next. This condition that the columns are orthogonal is absolutely necessary, and you can make simple examples next. We can look at one here. We take 1, 0, 0, 1, 1, 0, 1, 0, 1. Let P be the projection onto the first coordinate. Next. If we let A1 be 1, A2 and A3 are 0, B1 is 0, B2, B3 is 1, then AI PXI plus BII minus PXI is, in fact, the standard orthonormal basis. So this is a simple piecewise scaling that turns us into a Parseval frame when this very trivial example is not actually scalable. Excuse me, next. On the other hand, if we take the same vectors, and again, let P be the projection on the first coordinate, there's another way to scale this frame. Next. Suppose we let A1 equal A2 equal A3 equal 1 over the square root of 3. P is projecting on the first coordinate. So P of xi is now the vectors which all start with 1 over the square root of 3. We can again let B1 be 0, B2 equal B3 equals 1. Then it's sort of immediate that AI PXI and BI I minus P of xi are both Parseval. But we've lost this important condition, making the columns orthogonal. So this is actually not a piecewise scaling. So all this is trying to say is, if you have a frame in, say, Rn, R3, not number one, we'll see in a minute, not every projection will piecewise scale it. And number two, the choice of the constants AI and BI are quite critical to whether this is going to piecewise scale it. Next. The PB and projection AI BI are scalars. Let T1 be the analysis operator for AI PXI. T2 is the analysis operator of BI I minus PXI. Next. Then the following are equivalent. Next. This is a Parseval frame, meaning P, AI, BI are piecewise scaling this frame. Next. T1 plus T2 is an isometry. So this is not too hard to check in general, luckily. Next. T1 and T2 are isometries, and for every x in Rn, T1 of x is orthogonal to T2 of x. So these are somewhat straightforward ways to try to check whether I can piecewise scale this frame or not. Next. So why is this much better than regular scaling? Well, first of all, every frame in R2 is piecewise scalable. That's not surprising. What's surprising is it's piecewise scalable by every projection. You don't even have to pick the best one. You can pick the worst projection in R2, and you can piecewise scale this. And I think I gave the answer here. Next. Yeah, if P is a non-trivial projection, it's not possible that both P of x1 and P of x2 are 0, or P would not be a non-trivial projection. It's also not possible that P of xi is 0 and I minus P of xi is 0, or that would tell me xi is 0. It follows that there's an I unequal to j, so that Pxi is non-zero and I minus Pxj is non-zero. Next. So in particular, I can normalize each of these vectors and turn them into one-dimensional Parseval frames, set the other AJ and BI 0, and then I've now got a Parseval frame. So every frame in R2 is in fact piecewise scalable, and it's piecewise scalable by every non-trivial projection. Next. R3 is a little more complicated. Given 3 unequal vectors in R3, there is a projection P, so that P of x1 is orthogonal to P of x2. They're both non-zero, and I minus P of x3 is non-zero. Several things came up in this project which I didn't know, but I should have. I never actually tried to do this. That if you pick two arbitrary vectors in R3, you can always project them so they're orthogonal to each other. Next. So we can assume x1, x2 is 0 if we let u be lambda x1 plus x2 plus z, where norm z is 1, and lambda equals this. And we let I minus p be the projection onto u, then this p will actually solve this problem for us. It'll piecewise scale this. The point being here that this requires very special projections. That is, in R3, every three vectors are scalable, but not by every projection, just by some carefully chosen projections. Next. Every frame for R3 is piecewise scalable, but not by all projections. Next. I gave an example here. If we had only three distinct vectors spanning R3, if we choose the projection P in the above theorem, then these three vectors have to be an orthogonal set of vectors. It's the only way to scale three vectors in R3. Next. If we look at the canonical orthonormal basis, let xi be the frame given by this, E1, E2, E2 plus E3. Next. If P is the projection onto the span of E2 and E3, then P of X1 is 0, P of X2 is X2, P of X3 is X3. This set is not scalable. That's essentially immediate. So P does not piecewise scale this frame. So very simple frames in R3 there are some projections that won't piecewise scale them, but every frame for R3 will have a projection that piecewise scales it. Next. So here's the projection that piecewise scales this frame. Instead of projecting onto E2 and E3, X2 and X3, we project onto X1 and X2, and then it's not hard to show that we're going to piecewise scale this. Next. In general, if all the elements are a frame lying in an open quadrant cone, this family is not scalable. Next. So if xi spans Rn and xi of j is positive for all I and j, then for any projection P onto a proper subset of the canonical basis, P does not piecewise scale the frame. But this is just for n greater than or equal to 3. N equals 2, everything works. Next. Oh, but the trick here is I'm not even saying that if xi of j is positive for all I and j, then we can't piecewise scale. I'm saying you can't piecewise scale by projecting onto a subset of the canonical basis. You need a much more sophisticated projection than just the trivial one. After multiplying, actually, I don't even know what this is. Let me assume. Oh, this is just a proof of the original fact. Forget it. Let's go on next. Yeah, so next. Not surprisingly, if somebody's piecewise scalable, and we have a unitary transformation, if UP equals QU, UF is piecewise scalable with projection Q with the same scaling constants. Next. This is just saying the obvious, that unitary transformations will turn piecewise scalable frames into piecewise scalable frames. Now, the only reason this is mildly interesting is, as we saw before, if you take an arbitrary frame and try to project it onto a subset of the unit vectors, it may not scale it. But what this says is, if that irritates you, then first you can apply a unitary transformation to it. And if you apply the right one, you can now project onto a subset of the unit vectors and scale it. Next. A frame with canonical orthonormal basis EI is piecewise scalable if and only if, oh, that's what I just said. I didn't realize I'd written it down. Next. Suppose xi is a frame with a unit norm piecewise scalable frame with projection P. If AI, BI are scalars for which AI, P of xi, BI minus P of xi is the Parseval frame, then the sum of the maximum of the AI squares and the BI squares has to be pretty big. This is somewhat important in some of the applications because it's telling us that you can't start setting these vectors into tiny numbers. They have to remain somewhat large in general. Next. If AI, PXI, and BI, I minus P of xi are Parseval frames for P of Rn and I minus P of Rn respectively, then we also have inequalities in the other direction that have to tell us something about how the AIs and BIs can behave. Next. Actually, we only got 5 minutes. 5 minutes. I want to get to something. Let's skip this and move on and keep going. Major problem. This is actually, from my point of view, a major embarrassment. We introduced a new topic, piecewise scalable frames. The important thing is to show there's a lot of frames that are piecewise scalable. We got a ton of them in the paper. But the next obvious thing is to show there's non-piecewise scalable frames. And despite an infinite amount of work, we never found one. We can't find any frame that's not piecewise scalable. Now, it would be absolutely wonderful if they all were, but I don't believe that for a second. It's just that we weren't able to find one. But in the process of looking, we actually discovered some things that, again, I should have known, but I didn't. So next. It's easy to find non-scalable frames. We look at them. Next. It's almost impossible. Well, almost impossible. So far, it's been impossible to find non-piecewise scalable frames. Now, of course, we already know we can't do it in R2 and we can't do it in R3. So we already have to start at R4 before we do anything. Next. Yeah, next. This surprised me, and it came up while we were trying to construct a non-piecewise scalable frame. If we have a uninorm frame for Rn and the vectors are close, if P is any orthogonal projection, either PXI, PXJ is big for all I unequal to J, or I minus PXI, I minus PXJ is big for all I unequal to J. Now, excuse me, it's not surprising that for every I and J, one of these two is big because these are unit norm frames. It surprised me that actually you could show the moment PXI, PXJ is bigger than a half minus 4 epsilon for one I and J, that implies it's true for all I and J. The moment these vectors two vectors get separated, then they're separated from everybody in the projection. Next. Next. So the reason, well, I believe there's not piecewise scalable frames. And the way to get one, I claim, is here. If you have a uniform frame for which the vectors are very close together, if you take an orthogonal projection of rank between 2 and n minus 2, then F does not piecewise scale this frame. This is quite a complicated theorem, but this is important for the example. Next. I thought this would be a non-piecewise scalable frame. The reason being that the norm of every two vectors here are within n-1 epsilon. So if epsilon's small, all the vectors are arbitrarily close. So the only way to piecewise scale it is to use a rank 1 projection. And I thought we could show directly that no rank 1 projection piecewise scales this. Next. But the fact is, well, this is just checking that this is actually a Riesz basis for the space. Next. So we proceed by way of contradiction. Assume this is a Parseval frame. Next. By our earlier result, P must be rank 1. Next. And that means if we take these vectors, I should have said, we only have n vectors in Rn. If this is a Parseval frame, AI, PXI, BII minus PXI, if this is a Parseval frame, then in fact, it's an orthonormal basis. The only n element Parseval frame for Rn is an orthonormal basis. So therefore, if we interproduct these vectors, we're going to get 0. Next. So that means that if we could scale this, then AI, AJ, PXI, PXJ has to be minus BI, BJ, I minus PXI, I minus PXJ. And I thought that would be enough to show that, in fact, this doesn't work. Next. So one of the conclusions, we're actually out of time. One of the conclusions we drew from here is by changing AI and BI, we can actually assume in the case we're working in that I minus P of Xi inner product with I minus P of Xj is negative for every I unequal to J. And I was hoping that was going to be our contradiction, but it turns out I minus P is projecting out an n-1 dimensional space, and I have n vectors. And there's a theorem in Rn that says the largest number of vectors you can have that all have negative inner products is exactly n plus 1. And unfortunately, we're stuck right there. So in the end, I wasn't able to prove that this was not scalable. Next. We'll just jump to the end. You can keep jumping because we're out of time. Anyway, we need you to finish the proof. This is Maple the Lamb. Anyway, Janet and I wrote a murder mystery story set at the University of Missouri. I may have told you or not. Oh, I probably didn't tell you. My student Dorso wanted to be in the book. So unfortunately, we only had one free female character, and she was a serial killer. So my student Dorso is a serial killer in the book. And Maple is in the book also. This is Maple the Lamb. So anyway, this is sort of the beginning of piecewise scaling. I mean, we just wrote this paper. I think it has possibilities. It needs more work, and it desperately needs examples where you can't piecewise scale. And I don't know where to look. I thought the easiest way was to have the vectors so close together that the only possible piecewise scaling is the rank 1 projection. If you don't do that, even in R4, you end up in a huge mess. That is, how about rank 2 projections for 4 vectors in R4? They're each projecting out a 2-dimensional subspace. Is there any way to prove you can't always scale them? Somehow, you know. In other words, if you get past rank 1 projections, this becomes extremely complicated to try to construct a counterexample. So I still think the best place is sort of in the direction I headed. That example may not be the best. Actually, I made a variation of this where it's not triangular, but all the zeros are also epsilons, but with some plus and minuses to keep them independent. And that had the advantages that at least all the vectors have the same norm, and the norm of every 2 are still arbitrarily close. But still, I just haven't been able to do this. I spent more time on this than I can imagine, almost a month full time, and couldn't get anything to work. So anyway, thanks for the invite. If we have any questions,